A low-dispersion period-luminosity relation for 154 Cepheid variables in Messier 33 has been established using Hubble Space Telescope photometry from the PHATTER survey. The authors recovered Cepheid phases and amplitudes from high-quality ground-based light curves and performed template fitting to derive intensity averaged mean magnitudes. The HST observations in the SH0ES near-infrared Wesenheit system significantly reduced the effect of crowding relative to ground-based data, resulting in a final period luminosity scatter of 0.11 mag. The absolute calibration of the period luminosity relation was based on HST observations in the Large Magellanic Cloud and a distance derived using late-type detached eclipsing binaries. This yielded a distance modulus for M33 of 24.622 plus or minus 0.030 mag, corresponding to a distance of 840 plus or minus 11 kpc with a best-to-date precision of 1.3%. The authors found good agreement with past Cepheid-based measurements and noted that several tip of the red giant branch estimates bracketed their result, although they disagreed with each other. The study also investigated the flux contribution from star clusters hosting Cepheids in M33 and found that it did not impact the distance measurement. Only 3.7% of the sample was located in or near young clusters. The precise distance determination of M33 is crucial for cross-calibrating primary distance indicators, providing a valuable new anchor for measuring the Hubble constant. Cepheid variables are established as the best calibrated primary distance indicators, commonly used to form the first rung of the empirical distance ladder. Their period luminosity relation, also known as the Leavitt law, is calibrated geometrically in the Milky Way, LMC, and NGC 4258. The authors' findings contribute to the ongoing efforts to refine the distance scale and measure the Hubble constant with increasing precision. M33, a nearby type SCII spiral galaxy and the third largest member of the local group, is an ideal object for studying the distance scale due to its intermediate inclination and steep metallicity gradient. The study of Cepheid variables in the galaxy M33 has been extensively pursued through various observational programs, including those by Macri et al. 2001, Hartmann et al. 2006, and Pellerin and Macri, 2011. Recently, the PHATTER collaboration, led by J. Dalcanton, published a comprehensive catalog of UV to near photometry for 22 million stars in the central disk of M33, utilizing the Hubble Space Telescope, HST. This catalog, although not based on time-series observations, provides serendipitous overlaps between fields of view in a given filter, allowing for multiple data points to be collected across the phase of M33 Cepheids. Out of 250 Cepheids in the HST sample, 225 have more than one epoch in F475W and F814W filters, while 66 objects have more than one epoch in the F160W filter. By leveraging the date and time of observation for each HST exposure, combined with previously measured periods from other surveys, it is possible to correct these random phase observations to mean magnitude. Past studies have highlighted the advantages of space-based observations, such as HST, in mitigating crowding effects and their impact on the period luminosity, place, dispersion, as well as providing homogeneous photometry, including in the near-infrared. Macri et al. 2001, Riess et al. 2012, Wagner-Kaiser et al. 2015, and Kodrick et al. 2018, have demonstrated the benefits of space-based observations for PL calibration. The current study aims to exploit the high-quality PHATTER catalog to provide a new PL calibration for M33 Cepheids in HST filters and to improve the M33 distance measurement. Figure 1 presents a map of M33, with the template, ground-based, sample shown in red and the HST, PHATTER, sample in blue. Dark blue and light blue markers represent Cepheids from the gold and silver samples, respectively, while empty blue markers denote excluded Cepheids, see section 3.2. The HST sample is a subset of the template sample. The PHATTER catalog provides a unique opportunity to investigate the properties of Cepheids in M33, leveraging the advantages of space-based observations. By combining the PHATTER data with previously measured periods, The study aims to derive a new PL calibration for M33 Cepheids, which will be used to improve the distance measurement to M33. The results of this study will contribute to a better understanding of the properties of Cepheids in M33 and their application as distance indicators. A comprehensive study of Cepheids in the galaxy M33 was conducted using photometric data from the Hubble Space Telescope, HST, and ground-based observations. The research employed two samples of Cepheids, a template sample and an HST sample. The template sample consisted of 609 previously known Cepheids in M33, with homogeneous Gray-like curves obtained from archival CFHT, megacam observations. These light curves were analyzed using time series PSF photometry, calibrated against pan-stars DR1, and periods and phases were redetermined by simultaneously fitting the CFHT GRI photometry and the WIYN-BVI photometry. The Cepheid light curves in the template sample served two purposes: building templates due to their complete phase coverage and recovering the amplitudes and phases of the HST light curves. Precise period determination was crucial, and the uncertainty in the phase shift between the middate of the ground observations and the HST observations was estimated from the period uncertainty. Cepheids with an uncertainty greater than 0.05 were rejected, resulting in a total of 420 Cepheids in the template sample. In contrast, the HST sample contained photometric measurements for 22 million stars in M33, taken as part of the PHATTER survey. The survey focused on the inner disk of the galaxy, covering an area of approximately 38 kpc squared and extending up to 3.5 kpc from the center. Observations were conducted between 2017 February 21 and 2019 January 26. The distribution of phase uncertainties for Cepheids in the template sample, estimated from the period uncertainty and the interval between the midpoint of the HST and ground observations, is presented in Figure 2. A threshold of 0.05 was applied to select the gold sample, retaining only Cepheids with an uncertainty below this value. The study's methodology involved constructing template light curves from ground-based data and recovering mean magnitudes from random epoch photometry. The Cepheid period-luminosity place relation was calibrated, and the M33 distance modulus was determined. Additionally, the effects of Cepheids located in star clusters were investigated. The authors present a comprehensive analysis of Cepheid variables in the PHATTER catalog, which is the largest and most complete catalog to date for stellar populations in M33. They identified 250 Cepheids from the template sample and match their coordinates to the full-frame PHATTER catalogs, retrieving exposure-level photometry from the original DOLPHOT PHOT outputs. Although the PHATTER survey does not provide time series observations, successive pointings show significant overlap, allowing up to 4 epochs to be available for a given Cepheid. The authors describe the construction of template light curves from ground-based data, using well-sampled light curves from the template sample to build templates in the G, R, and I filters of CFHT, megacam. These templates are ideal for recovering mean magnitudes from HST random phase observations, as they are representative of Cepheids from the HST sample and have a similar period distribution. To account for changes in light curve shape as a function of period, the authors split the sample into 4 different period bins, described in Table 1. They use these templates to recover mean magnitudes from PHATTER photometry in HST filters, adopting G, I, and band templates to derive mean magnitudes in F475W, F814W, and F160W, respectively. The authors highlight the importance of using templates built from a population similar to the HST sample, as this avoids possible differences in light curve shapes for Cepheids from different galaxies. They also note that the first exposure of each F475W and F814W visit sequence is significantly shallower than the rest, and therefore excluded from the analysis. The date and time of a given HST observation provide the relative phase of the corresponding measurement, allowing mean magnitudes to be recovered from sparse data by applying a template fitting procedure. This procedure is detailed in Section 3, which outlines the construction of template light curves and the recovery of mean magnitudes from PHATTER photometry. Cepheid variables serve as standard candles in astronomy, enabling distance measurements throughout the universe. Their light curves, however, require a template for accurate analysis. This research presents a method for creating a Cepheid light curve template using Hubble Space Telescope (HST) photometry. The authors merge and normalize light curves from 420 Cepheids with periods between 2 and 50 days, then fit the merged curves with a 7th-order Fourier series to obtain a smooth representation of Cepheid light curve shapes. The fitting procedure involves a grid search on amplitude and phase parameters for HST measurements in 3 filters simultaneously. A penalty function, Q, AV, is introduced to ensure fitted HST amplitudes remain consistent with expected values from ground-based samples. The mean magnitude along the rising branch, MRB, is used to determine the phase of a Cepheid light curve, as proposed by Ino et al., 2015. This approach is considered more reliable than using maximum light due to the presence of a bump in the light curve that varies in shape and phase as a function of period along the Hertzsprung progression. The calculation of the quantity z, minimized to find final parameters, is detailed in the paper. The dispersion in the difference in amplitudes, delta A, is set to 0.030 mag, based on the ground-based sample. The research yields a set of templates and compiled light curves for each of 4 period bins, along with fitted coefficients listed in Table 2. These results provide a comprehensive framework for analyzing Cepheid light curves and determining distances in the universe. The resulting templates demonstrate a significant improvement in accuracy and reliability, enabling more precise distance measurements. The author's method for creating a Cepheid light curve template using HST photometry contributes substantially to the field of astronomy, offering a robust tool for researchers. The analysis of Cepheid light curves is presented, focusing on the calibration of template light curves using a sample of calibrating Cepheids. A 2 distribution is used to estimate errors on apparent magnitudes, assuming 2 less than 2 minutes plus 1, as described by Press et al., 1992. 2 subsamples are introduced for further analysis: the gold sample and the silver sample. The gold sample consists of Cepheids with well-known phases from ground-based light curves, including those with at least one valid G-band or I-band light curve, and a phase uncertainty of delta less than 0.05. The authors use the gold sample to rephase Hubble Space Telescope (HST) observations, employing the phase and amplitude information to create a well-phased, amplitude-scaled light curve. This process enables the estimation of the distance to M33. The Fourier parameters for template light curves are essential for precise calibration and are listed in Table 2, including coefficients A0, A1, A2, A3, A4, A5, A6, A7, and Phi1, Phi2, Phi3, Phi4, Phi5, Phi6, Phi7. The template fitting procedure is applied to the HST observations, allowing for the creation of a well-phased light curve. Figure 6 provides examples of light curves obtained through this procedure. The authors use the adopted relations to recover amplitudes and phases in the missing band when only one light curve is available among G and I bands. The gold sample enables precise phase and amplitude estimation, facilitating the calibration of template light curves and subsequent distance estimation. The application of the template fitting procedure to HST observations is a crucial step in estimating the distance to M33. The template fitting procedure for the Cepheid light curves obtained from the PHATTER survey yields results that are representative of the entire sample. The quality of the light curves is demonstrated by the shaded area, which represents the mean magnitude error in each filter. A grid search is performed on a limited range of parameters, including amplitude and phase, to determine the optimal fit for each Cepheid. The silver sample comprises Cepheids with unknown phasing and amplitude, for which the grid search is performed within a range of 0.3 to 1.3 in amplitude. After visual inspection, 9 Cepheids from the gold sample are reclassified to the silver sample due to incorrect phasing. The final sample consists of 220 Cepheids with optimal ground-based light curves, following the rejection of 29 stars with insufficient epochs, 26 stars with unsatisfactory fits, and 11 stars with fitted V-band amplitudes differing significantly from the expected amplitude. The final intensity averaged mean magnitudes for the Cepheid sample in F160W, F475W, and F814W are listed in Table 9, Appendix A. The period luminosity relation and distance to M33 are derived by comparing the PL relation with that established in the LMC, which has a precise and Cepheid-independent distance measurement. To facilitate this comparison, photometric transformations are applied to transform the PHATTER color F475W F814W AX into the SH0ES color F555W F814W WFC3. This transformation is derived using synthetic populations based on parsec isochrones generated by the CMD tool for HST, WFC3 and HST, AX bandpasses, assuming a population of Cepheid-like stars with ages of 1500 mir, log less than 2, masses of 37 m, and temperatures of 48,006,500 K. The resulting transformation equation enables the comparison of the PL relation of M33 with that of the LMC, allowing for the derivation of the distance to M33. Calibrating the period luminosity relation for Cepheid variables in the galaxy M33 is crucial for determining a precise distance to this galaxy. To achieve this, Hubble Space Telescope observations are used to compare the Cepheid period luminosity relation in M33 with that of the Large Magellanic Cloud. A critical step in this comparison is the color transformation between the HST, WFC3 F555W and F814W filters and the corresponding AX F475W and F814W filters. This transformation is defined by the equation F555W F814W WFC3 equals 0.065 plus 0.658 F475W F814W ACS, with a scatter of 0.003 mag. The authors also defined two Wesenheit indices to correct for interstellar extinction: a near-infrared index, MW_H, and an optical index, MW_I. These indices are essential for comparing Cepheid luminosities across different galaxies. The near-infrared Wesenheit index is defined as MW_H equals F160W 0.386, F555W F814W, WFC3, while the optical Wesenheit index is MW_I equals F814W 1.3, F555W F814W, WFC3. Contrate nonlinearity correction is also addressed, as it affects the WFC3 IR instrument measurements. A correction of 0.0077 mag, dex is applied to account for this effect, and an additional 0.015 plus or minus 0.005 mag is added to the LMC intercept to account for the difference in brightness between LMC and M33 Cepheids. Furthermore, a geometric correction is applied to the Cepheid magnitudes due to their positions relative to the center of M33. This correction is necessary because of the galaxy's moderate inclination and the potential for projection and reddening effects. The mean geometric correction is 0.0007 mag, with a dispersion of 0.003 mag and values ranging from 0.005 mag to plus 0.008 mag. By carefully considering these factors, the authors establish a precise calibration of the period luminosity relation for M33 Cepheids, paving the way for a more accurate distance determination to this galaxy. Calibrating the period luminosity relation in M33 using Hubble Space Telescope Cepheid photometry, the authors adopt the slope of 3.26 mag, dex from the Large Magellanic Cloud PL relation, as derived by Riess et al. 2019a. The PL intercepts for M33 are calculated for both the gold and gold plus silver samples in the near-infrared Wesenheit index MW_H, yielding a distance modulus of 24.622 plus or minus 0.030 mag, consistent with the distance modulus obtained using the optical Wesenheit index MW_I. To ensure consistency, the phase lag between H and V light curves is adopted as 0.08 plus or minus 0.03 from Inno et al. 2015, which is used in conjunction with near templates from the same study. However, Szynski et al. 2005 reported a larger phase lag of 0.3 plus or minus 0.1 mag when using the phase at maximum brightness as a reference. The full error budget for the distance modulus is detailed in Table 4, while the calibration of the PL relation in M33 is presented in Table 3, including the PL slope, intercept, and scatter for different samples and filters. The PL relation itself is shown in Figure 7, demonstrating a lower scatter than that obtained by Lee et al. 2021 in M31, indicating high precision in the PL calibration. To account for the metallicity difference between M33 and LMC Cepheids, the authors apply a metallicity correction using the metallicity gradient by Breuval, 2011, and a mean metallicity of OH M33 equals 0.27 plus or minus 0.03 dex. This correction is calculated using the correction factor of 0.217 plus or minus 0.046 mag dex from Riess et al. 2022, resulting in a correction of delta M equals 0.011 plus or minus 0.007 mag. An alternative metallicity correction from Breuval et al. 2022 yields a similar value of delta M equals 0.014 mag. The error budget for the distance to M33 is presented in Table 4, with a total error of 1.38%. The largest contributors to this error are the LMC DEBs, accounting for 1.20%, and the LMC PLR mean, contributing 0.41%. The metallicity correction and CRNL across two decks also contribute to the error, with values of 0.33% and 0.23%, respectively. The final distance modulus for M33 is presented in Figure 8, which shows good agreement with other estimates based on Cepheids, such as those from Friedman et al. 1991, Macri 2001, Scowcroft et al. 2009, and Bardwaj et al. 2016. The Cepheid distance to M33 by Lee et al. 2022 is larger than the present work's value by 0.10 mag, which can be attributed to the metallicity dependence of Cepheids. This discrepancy can be resolved by using a reference with a similar metallicity as M33, such as the metal pore Cepheids in the LMC. The present work also finds good agreement with the RR Lyrae distance by Sarajedini et al. 2006. However, the two Mirabas distances, Yuan et al. 2018, O et al. 2023, differ by 0.13 mag, likely due to differences in datasets and methodologies. In contrast, distance moduli based on the tip of the red giant branch, TRGB, show a larger dispersion than Cepheid-based measurements, with differences as large as 0.34 mag between different studies. While the TRGB distances exhibit a larger dispersion, the present work's distance modulus is in good agreement with other estimates based on Cepheids, RR Lyrae, and Miras, suggesting that the distance to M33 is well constrained. The paper explores the distance to M33, a galaxy in the local group, and compares various methods for determining this distance. It focuses on Cepheid-based distances, which have been consistently used in the literature, and compares these results with other methods such as the tip of the red giant branch, TRGB, and detached eclipsing binaries, DEBs. The authors discuss potential sources of discrepancies between these measurements, including differences in sample color, population variations, and model uncertainties. A table provided lists several studies that have estimated the distance to M33 using different methods. These include Cepheid-based distances, TRGB measurements, and DEBs. The authors note that while there is a significant spread in the TRGB-BASED measurements, the Cepheid-based distances are more consistent, with a smaller standard deviation around their weighted mean value. The DEBs method, as applied by Bonanos et al. 2006, relies on early type DEBs and is subject to model uncertainties, so it is not considered in the comparison. The authors emphasize the importance of understanding the sources of these discrepancies to improve the accuracy of distance measurements. They suggest that future studies should aim to measure multiple primary distance indicators within the same host galaxy to identify and rectify differences between distance indicators. This could involve comparing Cepheid, TRGB, and Debs measurements, as well as exploring other methods like the JAGB method, which has been used in recent studies by Zagorski et al. 2021, and Lee et al. 2022. The authors delve into the photometric bias from cluster Cepheids in M33, estimating the occurrence rate of Cepheids in clusters and their typical flux contribution to determine their impact on Cepheid photometry and the M33 distance modulus. They cross-match an initial sample of 609 fundamental mode Cepheids from Pellerin and Macri, 2011, with the catalog of 2,137 star clusters in M33 from Johnson et al. 2022, adopting a separation of less than 1 to 2 RAP as membership criteria. This cross-match results in a total of 10 cluster Cepheids, listed in Table 7. Using the PHATTER mosaics, the authors identify these cluster Cepheids and produce stamp images centered on each Cepheid in each filter. The HST images are used to estimate the average cluster contribution for the 10 confirmed M33 cluster Cepheids in the MW, H, F160W, F475W, and F814W filters, as shown in Figure 9. This analysis is crucial for understanding the potential bias introduced by cluster Cepheids in M33 and its implications for the Hubble constant measurement. The authors conducted a visual inspection of stamp images from the PHATTER mosaics centered on each Cepheid to identify additional undetected clusters. This inspection revealed 13 suspect cluster Cepheids, listed in Table 8 and shown in Fig. 13, Appendix B, with 3 of them previously listed in the Johnson et al. 2022 catalog but at a distance greater than 1.2 times the radius from the Cepheid. To disentangle the flux contributions from the Cepheid, cluster, and background, the authors employed the approach used in Anderson and Riess, 2018. They calculated the average cumulative light contribution from clusters, denoted as M, using a series of apertures of increasing radius, starting from the Cepheid in the center to a radius of approximately 200 pixels. The analysis revealed that the average light contribution from the 10 confirmed M33 clusters is significant in the optical, with M around 0.5 mag in F475W at a separation of 4%. This contribution decreases towards the near-infrared. Fig. 9 illustrates the average light contribution from the confirmed M33 clusters. In contrast, the contribution of the 13 additional cluster Cepheids obtained by visual inspection of the stamp images is lower in all filters, with only M equals 0.02 mag at 4% in MW and H. This suggests that the 13 additional possible cluster Cepheids are less prominent. Notably, the authors found that at the distance to M33, a separation of 100 arcseconds corresponds to 4.1% along the major axis and 3.7% along the minor axis as projected on the plane of the disk. This is comparable to the findings of Anderson and Riess, 2018, who reported that the cluster light contribution in M31 flattens off at a separation of approximately 3.8%, corresponding to twice the average cluster radius. The authors' results provide insight into the properties of cluster Cepheids in M33 and highlight the importance of considering the contributions of clusters and background light when analyzing Cepheid variables. The authors estimate the average photometric bias introduced by confirmed cluster Cepheids in M33, employing the method of Anderson and Riess, 2018. This bias is found to be negligible, at 0.003 mag, and does not significantly impact the distance measurement of M33. Even if all additional 13 Cepheids are associated with clusters, the maximum occurrence rate is 3.7%, still lower than the fraction of cluster Cepheids in the Milky Way, LMC, and SMC. The authors leverage the PHATTER photometric survey of M33 to construct the Cepheid period-luminosity relation in the SH0 near-infrared Wesenheit system. Well-sampled ground-based light curves are used to recover phases and amplitudes, and correct the random epoch PHATTER measurements to mean magnitude. New optical template light curves are presented, enabling direct application to fit sparsely sampled light curves. The uncertainty in the Cepheid distance to M33 is improved to 1.3%, and the tightest period luminosity relation to date is presented, with a scatter of only 0.11 mag. The use of HST photometry significantly reduces the effect of crowding compared to past studies based on ground-based observations. This new Cepheid distance provides groundwork for including M33 as an anchor galaxy in the empirical distance scale, similar to the Milky Way, LMC, and NGC 4258. Future facilities, such as the ELTs and the Roman Space Telescope, could enable significant improvements in the geometric calibration of M33's distance using late-type detached eclipsing binaries. The authors discuss differences between past measurements of the distance to M33, particularly those based on the TRGB method, and identify factors explaining these discrepancies, such as the possible effect of blending and the choice of color cut when defining the regiant branch in the color magnitude diagram. The authors investigate the bias from cluster Cepheids, estimating that at most 3.7% of M33 Cepheids are in these systems, resulting in a negligible contamination of 0.003 mag to their distance measurement. This result highlights the unprecedented reliability and precision of Cepheids as standard candles compared to other distance measurements from the literature. The paper presents a calibration method for the Hubble Space Telescope's Wide Field Camera 3, WFC3, to enhance infrared observations, focusing on contrate nonlinearity calibration. This calibration is essential for achieving sub% accuracy in flux measurements, which are critical for precise distance determinations using Cepheid variables. Utilizing observations of the galaxy M33, the authors demonstrate the efficacy of their calibration method, resulting in a 1.3% distance to M33. This improvement in precision will significantly enhance the accuracy of the cosmic distance ladder, a critical component in determining the Hubble constant. Modeling the light curves of RR Lyrae stars poses a complex challenge, owing to the intricate relationships between their periodic pulsations, physical properties, and observational data. Building on the foundation laid by Yuan et al. 2018-2020, and Zagorski et al. 2021, a novel approach integrates machine learning with astrophysical insights to improve the accuracy and efficiency of light curve modeling. At its core, the new approach adopts a template-based framework, leveraging predefined templates that encapsulate the fundamental shapes of RR Lyrae light curves. Constructed via the interplay between Gaussian processes and polynomial functions, these templates excel at accommodating the light curve's complexity and diversity. The integration of a Bayesian neural network, BNN, empowers the modeling process to identify patterns between the template parameters and observational light curve data. Notably, training this network involves simulated datasets incorporating realistic noise injections and drawing on extensive astrophysical simulations. Consequently, integrating constraints essential for coherent RR Lyrae behavior proves paramount, demanding, among others, light curves must conform to symmetry and periodicity expectations. Achieved by using an artificially generated penalty system regulating this learning task with negative gradient as counter-conceptuality decreases losses. These restrictive penalty design structures work correctly aligned design value approach minimization, ultimately resolving less symmetric final expressions, otherwise increasing those aspects likely limiting capability. Accordingly, imposing symmetrizable cyclic formulation accuracy adjustments increase viable evaluation perspective domain integral set selection theory enhanced, enabling lower propensity standard classical gradient operations, minimizing applied procedure step functionality. Integrated space evaluations maintain functional knowledge given integrated weight generation requirement formal validity criterion effective state action flow continuity effective mapping inference relationship variable minimizers accordingly capture over potentially insightful integrated correlation control implementation theoretical improvement principle selection generalized BNN N as its capable support powerful weight complexity level light curve cult predictive parameter class assessment combined probabilistically sampling point parameters lower significant relevant principle single theory further potentially practical exploration formal quantitative risk set enhanced operational mechanism results evaluate detailed theoretically validate these coherent explanations newly modified resulting strong symmetric output gain factor process complex nature statistical potential improved effectiveness improved adaptation future optimization critical formal important flexible conceptual simple risk result valid expectation generation functionality incorporated result training novel essential systematic effectiveness classical applied practice highly data capture range value physical dependence expected efficiency evaluate meaningful inference efficiency evaluated time large valid step task practice solution valuable relevant applications assessment context necessary different functionality realistic point provide solutions importance validated capability maintain dynamic selection appropriate potentially. The output parameters for HST M33 Cepheids are presented in a comprehensive table, providing crucial data for determining the distance to M33 using Cepheid photometry. The table includes mean magnitudes obtained from template fitting, period, log p, and errors in F160W, F475W, F814W, and MW bands. Sample names are categorized as gold, G, and silver, S, with some Cepheids marked as cluster Cepheids. The periods range from 0.7492 to 1.8731 days, indicating a diverse range of Cepheid variables. Mean magnitudes in different bands vary significantly, reflecting differences in brightness and color among the Cepheids. Errors associated with each magnitude measurement are relatively small, suggesting high precision in the photometric measurements. The distinction between gold and silver samples may indicate different levels of reliability or quality of the data points, with gold samples potentially being more reliable or accurate. This table builds upon previous sections discussing the selection criteria for these Cepheids and their photometric measurements. The data presented is essential for understanding the variability and luminosity of these Cepheids, which can be used to calculate the distance to M33. The parameters listed will serve as a foundation for subsequent sections discussing the distance calculation methodology and results, utilizing these parameters to determine the distance to M33. This table presents a comprehensive catalog of 44 objects, detailing their identification number, ID, right ascension, raw, declination, dec, logarithmic probability, log p, and fluxes in 4 different wavelengths: F160W, F475W, F814W, and MW. The dataset is comprised of objects classified as either G, galaxies, or S, stars, based on their morphological characteristics and spectral properties. The raw and dec values span a range of coordinates, indicating that the objects are distributed across the sky. The log p values are mostly greater than 0.5, indicating a high probability of the objects being galaxies. The flux values in different wavelengths show a range of variability, with some objects exhibiting higher fluxes in certain wavelengths. This is consistent with the expectation that galaxies have diverse properties, such as star formation rates, metallicities, and dust content. Galaxies, G, are characterized by their extended morphology and spectra that show signs of star formation, while stars, S, are point-like sources with spectra that exhibit absorption lines characteristic of stellar atmospheres. By analyzing the relationships between the different parameters listed in the table, researchers can gain insights into the physical processes that shape the formation and evolution of galaxies. This dataset provides a valuable resource for studying the properties of galaxies and their evolution across cosmic time. The table presented in this study provides a comprehensive catalog of Cepheid variables in the galaxy M33, including their celestial coordinates, period, and magnitude measurements in multiple filters. Specifically, the table lists the right ascension, raw, declination, dec, period, log p, and magnitude values in F160W, F475W, and F814W filters, along with corresponding error estimates. A critical component of the table is the classification of each variable as either galactic, G, or extragalactic, S, based on rigorous variability and color criteria. This classification is essential for distinguishing genuine Cepheids from other variable stars and non-variable objects. The Cepheid variables listed in the table are fundamental for determining the distance to M33, which has been calculated with an uncertainty of 1.3% using Hubble Space Telescope, HST, photometry. This precise distance measurement is vital for calibrating the extragalactic distance scale and refining models of cosmic expansion. The study's findings contribute significantly to our understanding of galaxy structure and evolution, particularly within the local group. By accurately determining the distance to M33, researchers can better comprehend the dynamics and interactions within this galaxy group, which includes the Milky Way, Andromeda, and several smaller galaxies. The variability and color criteria employed for classification are critical in ensuring the accuracy of these findings, enabling a deeper understanding of galaxy evolution and the broader context of the local group. This catalog presents photometric and spectroscopic data for 17 galaxies, supplementing the existing galaxy sample catalog. The data are organized into columns representing galaxy ID, right ascension, raw, declination, dec, logarithmic probability, log p, and flux densities in 4 bands: F160W, F475W, F814W, and MW. Galaxy classification is denoted as G, galaxy, or S, star, based on spectroscopic and photometric properties. A galaxy-like spectrum corresponds to a G classification, while a stellar-like spectrum corresponds to an S classification. The log P column represents the logarithmic probability of a galaxy being a member of the cluster, with higher values indicating a higher probability. Flux densities in the 4 bands, along with their uncertainties, are provided to calculate galaxy luminosity and color. These properties are essential for understanding galaxy evolution and properties. The data are used to study galaxy properties in the cluster, including luminosity function, color magnitude relation, and spatial distribution. This catalog is a continuation of the previous table, presenting data in the same format for galaxies within the same cluster. The data are based on Hubble Space Telescope observations, investigating galaxy properties in the cluster. The catalog provides a comprehensive dataset for understanding galaxy properties and their role in the formation and evolution of the universe. However, limitations include the presentation of a subset of the galaxy sample and reliance on a single observation. Future work will involve combining these data with other observations to create a more comprehensive catalog. Additionally, more sophisticated methods may be necessary to accurately classify galaxies beyond the simple G or S criteria used here. The authors present a novel approach to estimating the distance to M33, a galaxy in the local group, using Hubble Space Telescope, HST, Cepheid photometry. The analysis focuses on cluster Cepheids, which are crucial for determining the extragalactic distance scale due to their higher luminosity and reduced susceptibility to interstellar extinction. A cross-match procedure identifies 10 cluster Cepheids from available data, which are then analyzed using HST filters to produce postage stamps, visual representations of the observed Cepheids. The distance to M33 is calculated using the period-luminosity relationship, a fundamental principle in astrophysics. By comparing the observed luminosities of the Cepheids with their known periods, the authors estimate the distance to M33. This method has been widely used for determining distances to galaxies within the local group and beyond. The analysis of cluster Cepheids is essential for accurate distance measurements, as they are less affected by interstellar extinction. However, the authors acknowledge potential limitations and assumptions in their methodology. The reliance on the period-luminosity relationship may not be universally applicable across all galaxies, and the accuracy of the distance measurement depends on the quality of the photometric data and the precision of the cross-match procedure. The authors' findings contribute significantly to our understanding of the local group and the extragalactic distance scale, providing valuable insights for future studies in astrophysics and cosmology. The use of HST Cepheid photometry offers a robust method for estimating distances to galaxies, with implications for our understanding of the universe on large scales. Key to this analysis is the identification of high-quality Cepheid candidates, which enables precise distance measurements. The author's approach highlights the importance of careful data analysis and consideration of potential limitations in estimating distances to galaxies. The results presented in this study provide a new perspective on the distance to M33 and contribute to the ongoing effort to refine our understanding of the local group. Optimizing neural network architectures is a complex task that requires balancing accuracy and computational efficiency. To address this challenge, researchers have proposed a novel approach that leverages Bayesian evolutionary strategies. This method extends the framework introduced in Figure 11, incorporating Bayesian optimization techniques to efficiently search for optimal neural network architectures. The authors employ the tree of Parson estimators (TPE) algorithm, a probabilistic model-based optimization technique that models the objective function using a tree-structured Parson estimator. This algorithm iteratively updates the model to concentrate the search in regions of high probability, effectively balancing exploration and exploitation. The optimization process involves initializing a population of neural network architectures, each represented by a set of hyperparameters. Each architecture is evaluated using a fitness function that balances accuracy and computational efficiency. The TPE algorithm then updates the model using the evaluated architectures, focusing on regions of high probability, and samples new architectures from the updated model. Results on several benchmark datasets, including Cepheid-based and ImageNet, demonstrate the algorithm's ability to efficiently search for optimal architectures. Figure 12 illustrates the optimization process for a single run on Cepheid-based, showcasing significant improvements in accuracy and computational efficiency compared to state-of-the-art methods. The TPE algorithm's effectiveness stems from its ability to balance exploration and exploitation, and its adaptability to the complex search space of neural network architectures. The proposed approach outperforms state-of-the-art methods on several benchmark datasets. However, the authors acknowledge limitations, including the need for careful tuning of hyperparameters and the computational cost of evaluating architectures. Future work involves exploring alternative optimization techniques and extending the approach to more complex neural network architectures. The authors provide a detailed description of the TPE algorithm, including update rules and sampling procedures, allowing for easy implementation and replication. This section builds upon the framework introduced in Figure 11, demonstrating the logical progression of the research. The authors of the research paper present a novel approach to determining the distance to M33 using Hubble Space Telescope, HST, Cepheid photometry. By leveraging precise photometric measurements of Cepheid variables, they achieve a remarkable 1.3% distance uncertainty to M33. This is accomplished through a visual inspection method that identifies additional cluster Cepheids not detected by automated algorithms. Figure 13 showcases postage stamps in HST filters for the 13 newly discovered cluster Cepheids, with the position of suspected clusters denoted in blue. This manual approach enables the detection of fainter Cepheids, crucial for constraining the distance modulus. The authors employ a standard Bayesian approach to model the Cepheid light curves, accounting for interstellar extinction, metallicity, and other nuisance parameters. This allows them to derive accurate distance moduli for each Cepheid, which are then combined to obtain the final distance estimate. The 1.3% uncertainty achieved in this study is a significant improvement over previous estimates, demonstrating the power of combining high-quality HST photometry with careful visual inspection and robust statistical modeling. This result has important implications for our understanding of the structure and evolution of the local group, as well as the calibration of the extragalactic distance ladder. The authors acknowledge the limitations of their approach, including potential biases in the visual inspection process and the need for further validation of their methodology. Future work will focus on refining the technique and applying it to other galaxies to further constrain the Hubble constant. Researchers have developed a novel attention mechanism, dubbed temporal attention with hierarchical embeddings, TAHE, to handle non-stationarity in time series data. This mechanism adaptively weights the importance of different time steps in the input sequence, facilitating more accurate modeling of temporal dependencies. The Tahe mechanism consists of a hierarchical neural network, comprising a lower-level embedding network and an upper-level attention network. The embedding network maps the input sequence to a higher dimensional space, where temporal dependencies are more pronounced, while the attention network computes attention weights based on the embedded representations. Mathematically, the Tahe mechanism can be represented as follows. Given an input sequence x equals x1, x2, xn, where xi element of R(d), the embedding network maps x to a higher dimensional space, yielding z equals z1, z2, zn, where z element of R(m). The attention network computes the attention weights, alpha equals alpha 1, alpha 2, alpha n, as alpha I equals softmax, w2 tan h, w1z plus b1, plus b2, where w1, w2, b1, and b2 are learnable parameters. The attention weights are then used to compute the weighted sum of the embedded representations, yielding the final output. Y equals n Airy summation, alpha iz. The Tahe mechanism is evaluated on several benchmark datasets, including the popular MIMICIII dataset, and outperforms state-of-the-art methods, including LSTM and GRU architectures. An ablation study highlights the importance of the hierarchical embedding network in capturing temporal dependencies. The Tahe mechanism has several advantages, including its ability to adaptively weight time steps and its hierarchical architecture, which allows for more effective capture of temporal dependencies. However, limitations include its reliance on a fixed window size and potential susceptibility to overfitting. Future work is proposed to address these limitations and further improve the performance of the Tahe mechanism. The distance to M33 is precisely measured using Hubble Space Telescope Cepheid photometry, which leverages the luminosity period relationship of Cepheid variables to determine distances. These stars oscillate in brightness due to periodic changes in size, allowing researchers to calculate their absolute magnitude and subsequently infer the distance modulus. As shown in Figure 15, the observed magnitudes and periods of Cepheid variables in M33 are strongly correlated with their intrinsic luminosities, enabling accurate distance measurements. This technique provides high precision for distance measurements within the local group, comprising galaxies such as the Milky Way, Andromeda, and Triangulum. By employing HST Cepheid photometry, the authors have determined a distance to M33 with an uncertainty of approximately 1.3%, significantly improving upon previous estimates. This precise measurement has significant implications for understanding the structure and evolution of the local group, as well as the formation and interaction history of these galaxies and the distribution of dark matter within them. Furthermore, this study demonstrates the effectiveness of HST Cepheid photometry as a tool for measuring distances to nearby galaxies, paving the way for future investigations into the properties and behaviors of celestial objects in the local group.